The main object of study we're going to be dealing with here is systems of linear equations. So when we finished the differential equations chapter, we studied linear differential equations, and linear algebra is the tool that we use to study linear differential equations. So by a system of linear equations, I mean something like this. This probably make your brain itch a little bit, but you've seen stuff like 2x plus 3y plus 7z is equal to 4, minus 5x plus y plus 8z is equal to 2, 6x plus 0y's plus 12z's is equal to minus 15. You in the past would have learned lots of methods for working with things like this. You may have been taught it as Gaussian elimination, but the idea is you choose a variable to eliminate, and then you combine these two into a new equation. Sometimes people learn this with Roman numerals, like, oh, now it's in Roman numeral equation 1 and Roman numeral equation 2. So you would combine these together into equation 1 and equation 2 by eliminating the same variable. Now you got two variables, then you got to do it again, and you sort of trace your way through until you can back substitute. So we're going to try to take that process and make it way more efficient and set it up in the way that computers do it as well. So the first step to making this more efficient, to solving linear systems more efficient, is actually to translate this into the language of matrices. Matrices in linear algebra are sort of the core language of contemporary math because, like, these are easy for computers to do, basically. And the first observation is, because of the way that vectors work, I could translate this system of equations in two different ways. I can put it in sort of a vector form by observing that I could get the same information about x, y, and z out by writing it down as 2 minus 5, 6 times x plus 3, 1, 0 times y plus 7, 8, 12, z is equal to 4, 2 minus 15. So there's a vector form of the equation. That's one of the, I pointed out last time, that's called a linear combination. So this interpretation of the question is I have three planes sitting in space, and I'm looking for points that are in all three planes at the same time. This interpretation of the equation is I would like to find a linear combination of three vectors that adds up to that vector. Same question, right? So the answer is the same, but the interpretation is different. The other thing we could do, now that we know about matrix multiplication, is we can put this into matrix form. So in matrix form, I could observe that this same setup, or this vector equation, has the same answers that this does. 2, 3, 7, minus 5, 1, 8, 6, 0, 12, times x, y, z is equal to 4, 2, minus 15. That's the matrix form of the equation. You can see it has the original equations inside of it, because the way matrix multiplication is defined, you would write 2x plus 3y plus 7z, which is this left-hand side of this equation. And likewise, minus 5x plus 1y plus 8z, right? So that carries these equations as part of it. Just to get some terminology here, this is called a coefficient matrix. Because it's the coefficients of the variables. This is often called the vector of unknowns. And then I don't really know a consistent name for the right-hand side. Some people just call this the right-hand side vector. You might call it the vector of knowns or the output vector. So the last step that we could make here, if I'm trying to be as efficient as possible, is I could just take the variables out of this picture entirely and just record the structural, the numbers with the understanding that if I wanted to, I could translate back into a set of equations again. So I could write this as an augmented matrix, is what this is called. By taking the coefficient matrix, 2, 3, 7, minus 5, 1, 8, 6, 0, 12, and augmenting it with the solution column, 4, 2, minus 15. So if I tell you that a matrix is an augmented matrix, what I mean is you're supposed to interpret this column as being the right-hand side of a set of equations, and everything over here is a coefficient matrix. So the point of this type of linear algebra is there's a lot of busy stuff that's up here that's not actually contributing much to what's going on. If I could work with a system of equations by just working directly with a matrix, it would be significantly more efficient, and computers are much better at working with arrays than they are at lists of equations. So there's just a couple pieces of vocabulary that we need to pick up here before we go on to how to work with these things specifically. So if you have, given a system of equations, and let's put it in matrix form, so AX is equal to B. The system is called homogeneous if that right-hand side vector is all 0. So if the system of equations is just everything is equal to 0. It's called inhomogeneous if that vector is not 0. And then we say a system is consistent if it has a solution, and inconsistent if it has no solution. So let me write down an example of an inconsistent system, and then we'll move on to start talking about what we need in order to use matrices to solve systems of equations. So if I write down a system like, so I'm going to write this matrix down. So this is an augmented matrix. And an augmented matrix in practice might look something like this. 2, 3, 1, 4, 6, 10. Now, if I translate that back into a system of equations, since it's an augmented matrix, I know that these are the right-hand sides of the equations, and these are the coefficients. The columns correspond to different variables. I can call them x and y, or x1 and x2. It doesn't really matter. I'm going to name this the x1 column and the x2 column this time, instead of x and y. And if I was going to translate this back into a system of equations, the system it would represent would be 2x1 plus 3x2 is equal to 1, coefficients equal to the right-hand side, and 4x1 plus 6x2 is equal to 10. So the augmented matrix translates back into a system of equations. Now, this system of equations has no solution. To ask for a system of equations to be satisfied simultaneously is to ask for there to be a point on both of them. These are parallel lines. So if you plotted these would be parallel lines. Parallel lines don't cross. So there's no point that can satisfy both of these equations at the same time. If you did substitution or something, you'd end up with an equation that was impossible, like 5 is equal to 1. Okay? So this is inconsistent. All right, that is basically all of 2.3. 2.3 is a vocabulary chapter. Yep.
Will the line separating the furthest right?
Typically that won't be there. Okay. So if I give you a matrix and say it represents a system of equations, you can just draw the line in if you want to. So the book, I think, will a lot of times suppress the line. Does it actually draw them in? Okay, yeah. So one way or another, like any matrix that you write down can always be interpreted as an augmented matrix with the rightmost column equal to the sort of solution vector. Yeah, any matrix you can view any matrix as an augmented matrix. Yep. That's actually a powerful way to look at what matrices are actually doing, is to think about them that way. All right. So in 2.4, nope. You can always look at it as an augmented matrix. You can always impose any, like every matrix, no matter what, always represents a system of linear equations, always. Even if it doesn't come with that interpretation, you can always give it that interpretation. So normally when we're working with these things, we start with a linear system and we write down the augmented matrix that goes with it, or I tell you the matrix is augmented. But if I just came along and knocked on your door and handed you a matrix without telling you what it was, you could view it as representing a linear system in a productive way. All right, so 2.4, how to use row reduction of matrices to solve systems of equations. Okay, so I'm going to write down a simple set of linear equations of the sort that you would have seen in an earlier class. And then I'm going to make an observation about matrices. So I could consider the system x1 minus 2x2 is equal to negative 1, and minus x1 plus 3x2 is equal to 3. And I might ask, hey, I'm going to solve this system. Now, in earlier classes, you have learned about method of elimination and the method of substitution. I'm going to walk through an elimination method here, but organized in a very specific way. So I'm going to think about this equation here as row 1 of a system of equations, and I'm going to think about this as row 2. And I'm going to record the steps that I'm doing to change my system of equations into a new system of equations. So one observation that you would have made in earlier classes was, well, I could eliminate x1 very easily because if I add those equations, the x1 disappears. So if I was going to write that step down formally, I might write, I want to get rid of equation 2, and the way I'm going to replace row 2 is I'm going to replace it with the sum of row 1 and row 2. And if I wanted to, I could write down mathematically what row 1 plus row 2 is. Well, I'm not going to do that yet. We'll wait until we get to the matrix translation. So what that says is I should get rid of the second equation and replace it with the sum of the two equations. The first equation is unchanged. The second equation I get by adding the two equations together. Since it's a linear equation, I just add like terms. So x1 plus negative x1 is 0 x1s. 3x2 plus negative 2x2s is 1x2. And 3 plus negative 1 is 2. So notice that I know what x2 is now. In your earlier classes, this would be sufficient to stop, right? You know x2 is equal to 2, so you could back substitute into the first equation to figure out what x1 is. I could, however, go further. I might look at that and say, I don't want to back substitute. I'm going to keep eliminating, and now I'm going to go backwards and I'm going to eliminate x2 from the first equation. So I could continue by saying, okay, well, what if we took row 1 and we got rid of it and we replaced it with row 1 plus twice row 2. Because if I multiplied row 2 by 2 and added it to row 1, the x2s would disappear. Right? They won't be there anymore if I do that. If you do that, now, okay, so row 2 got left alone, so we still have an x2 is equal to 2. Row 1 is now supposed to be twice row 2 plus row 1. So 4 plus negative 1 is 3. And 2x2 plus negative x2 is 0 x2s. And 0 plus x1 is x1. And now there's nothing left. I could just read the answer off. So I eliminated in the forward direction to get me x2. And I can keep eliminating by going back and getting rid of all the rest of the x2s. And that tells me the answer. So that system of equation is solved by x1 equals 3, x2 equals 2. So the observation I want to make here is there's nothing novel about what I did except the way I'm organizing it. And the only reason I'm organizing it this way is I can do exactly the same thing to the augmented matrix that represents that system. So if I had started with this but in the augmented matrix form, I would have started with this. 1, minus 2, minus 1, minus 1, 3, 3. That represents that system of equations. If you like, I'll put the line in. Now, if I do exactly the same operations here, row 2 gets replaced by row 1 plus row 2. Okay, so row 1 got left alone. So 1 minus 2 minus 1. That's not row 2, it's row 2. Sorry. So that says I'm going to replace row 2. So row 2 is replaced by the sum of the rows. What a lot of people like to do in steps like this is actually write down what they're doing. So row 1 is 1 minus 2 minus 1. And row 2 is minus 1, 3, 3. And if you add those two together, you get 0, 1, 2. And notice the matrix we wrote down here is the matrix for the equations. We get the same thing. I could work with the equations, or I could have just done it directly with the matrices. I've done nothing different. If I proceed with the next step, row 1 is replaced by row 1 plus 2 times row 2. What we're actually doing there is, okay, so what's row 1? 1 minus 2 minus 1, that's row 1. And twice row 2 is equal to 0, 2, 4. And if I add those together, I get, 1, 0, 3. So I could have saved myself a whole bunch of fuss over there writing x1s and x2s all over the place and trying to make sure that my columns are lined up correctly just by working with the information that mattered, which was the coefficients and the solution vector. And when I get to the end, I can reinterpret this back as a system of equations. This would say x1, 1x1 plus 0x2s is equal to 3, and 0x1s plus 2x2s, plus 1x2 is equal to 2. I just read the solution to the original equation off. So there's no reason when I'm working with linear equations ever to write down the equations themselves. I can just work with the matrices. So the goal for the class, for this particular part of the class, is we want to come up with an algorithmic way of taking a system of equations, turning it into a matrix, and then coming up with some sort of algorithm that will let us produce something that tells us the answers. And it needs to be something stable, so like an actual formal algorithm. If you guys remember when you learned Gauss elimination, it's messy. It's like, I don't know, do I eliminate x, y, or z, and I got to make sure I eliminate the same thing from both equations. And then I have this other set of equations I have to solve. Like, this is not like that. This is supposed to be a clean algorithm for doing what you learned in earlier classes is kind of a mess. All right, so that's the goal. So the first thing we're going to do is we're going to define the set of things that we're actually allowed to do to a matrix. I want operations that don't change the answer to the equations. So these are called elementary row operations. There's 3 of them. So, given a matrix A, the 3 row operations are 1, I can swap 2 rows. So an example here might be if I had the matrix 1, 1, 0, 1, I could do switch the positions of row 1 with row 2. And that would give me 0, 1, 1, 1. Doesn't matter what order the equations come in, right? I can think of an equation being first or second and change the answers to the equations. Instead of swapping 2 rows, I can scale a row. So if I have the matrix 1, 1, 0, 1, I could write down something like take row 1 and replace it with 3 times row 1. So take a row and expand it. Multiplying an equation by a scalar on both sides doesn't change the answer to the equation. So the output here would be 3, 3, 0, 1.
Why do you do it where it's like you put R1?
You can put R1 on like any side you want. I'm identifying the row I want to replace and then the operation I'm doing to do the replacing with. If you want to do it in the other direction because it feels more natural to you, do it the other way. Yeah, I could do 3 row 1 becomes row 1. Like,
Does it like point the arrow in the
Yeah.
other direction, or does it? So that just
It won't matter.
Okay.
And step 3, and this is the most important one, I can replace a row with the sum of that row and a multiple of another row. And we did that all over here. That's what this operation was, right? I took a row and I replaced it with the sum of that row with a multiple of another row. So I could do something like 1, 1, 0, 1, and maybe I take row 1 and I replace it with row 1 plus 3 times row 2. And that would get me 1, 4, 0, 1. Yep.
What's like the reason that you know you can do that?
So the reason that this actually works, and I have to teach you about invertible matrices before I can make this rigorous. Each one of these operations is actually multiplication by an invertible matrix. That's basically what it is. I'm taking my coefficient. So this is an advanced question, but the idea is, if you had taken this original like setup right here, if I took 1 minus 2 minus 1, 3 times xy was equal to minus 1, 3, the matrix that does this, take row 1 and replace it with row 1 plus row 2, but leave row 2 alone, is this actually has a matrix form, which is 1, 1, 0, 1. Row 1 is 1 of row 1 plus 1 of row 2, and row 2 gets left alone. So you multiply both sides of the equation by this matrix, and it actually does that row operation. So every row operation is just multiplication by a matrix that I can undo. And notice when you do that, it doesn't actually change the answers to the equation. The x and y are the same because you multiply both sides by the same thing. So, I mean, I can make this more concrete when we know about invertible matrices, but the reason I'm sort of waving my hands here about why these are legal is because I have to write them down as matrix multiplications to make this precise. But it's a great question. Okay. The other answer is, the reason that I write them this way is because these are also related to, you guys remember determinants of matrices? How determinants say something about the size of a parallelogram? Each one of these operations has a different effect on the size of the parallelogram the matrix determines. This one changes the sign of the determinant by -1. This one changes the size of the determinant by multiplying by the same scaling factor. And this one doesn't change the size of the determinant, which is weird. Yeah.
If you were to add row 1 and row 2, why couldn't you replace row 1? Or do you always have to replace row 2?
You can replace any row you want. Any row can be replaced with a combination of any other rows. So if I want to give you an example of a bigger, here, let's write a bigger matrix down. This is a good question. So let's pick a nice fat matrix, like 1, 0, 3, 2, 10, 0, 0, 1, 6, 14, 0, 1. This is why computers exist, by the way. 2, 16. Pick any, what row do you want to multiply to add to what row, right? Give me a row operation.
Just any?
Pick a row that you want to replace. Which row?
Row 2.
Row 2. And what do you want to replace it by? Now, remember, the operation means already you know that you have to be combining. You can't throw the information in row 2 away, which is why it needs to be in part of what you're replacing it with. So plus what?
Row 3.
Do you want a multiple of row 3 or just row 3?
2 row
2 row 3.
Wait, can you not just add you can't just add 2 other matrices together to get another one?
What do you mean? You can add 2 rows to get another row.
Does that do anything for you? Like if you have 2 rows and you add them together and you get a third row, does that do anything?
Oh, do you want to change the matrix by putting more information in?
Yeah.
So that doesn't give you any new information about the equations, right? Because you're including extraneous information at that point. There's nothing new that you've done by doing that. So, yeah, the way to think about this is these are manipulations that keep the number of equations the same and don't change the solutions. That is what these operations are doing. Okay? So we're not adding information, we're not taking information away, we're leaving the exact same amount of information we started with, and we're trying to drill down to solutions. So that operation in this case would be, okay, so I'm going to write this down. So row 2 is 0, 0, 1, 6, 14, and that's row 2. And then row 3 was, so twice row 3 is 0, 2, 6, 4, 32. So if you add those together, you get the new row 2. So this is going to be row 1 got left alone. Row 3 got left alone. And row 2 is now 0 plus 0, 0 plus 2, 6, 1 plus 6, 6 plus 4, and 14 plus 32. I got a C in college because I took a circuits class, which is all about doing this, and I blew the row reduction on part A of a problem, and then I got every other part that came underneath it wrong because I made a mistake doing this. These are easy to screw up. Be careful.
That's cool.
It is. Now, the thing to keep in mind here is hardly ever in practice are you going to ever be asked to do this by hand. So this is you learn how to do it by hand now. You do it for this class and all of your basic science and engineering classes once, and then for all the rest of time, you have a computer that does it for you. So, yeah.
So we just always by hand on the test.
So I might have you hand row reduce one matrix ever on an exam, and it won't be anything other than show me how to row reduce this matrix by hand. And all the rest of them, I'll just give you the matrix and its row reduced form, and you can just interpret the answer instead of computing it. Hand row reducing matrices is painstaking and error prone. Yo.
What kind of solution would you come out with if your system of equations it didn't have like one solution? You have three rows.
Okay. So you've seen in earlier classes, like when you guys learned linear systems in the past, you learned consistent and inconsistent systems, and then you learned like systems that had unique solutions and systems that had infinite solutions. So if you think about these as representing linear equations, if I wrote something down like 3 systems, I could have 3 planes that are stacked up like this that are all parallel to each other, in which case the matrix for those planes would be inconsistent, right? I could have all 3 of the planes cross each other like this. So there's 2 planes, maybe there's a third one that cuts through like this. So like 3 corners of the room, right? Like there's one solution, it's on all 3 planes that's right there, right? This would be inconsistent system of linear equations. This would be a consistent system with one answer, but also there's no reason why I couldn't do this, where I have 3 planes that are set up sort of where they have a line of solutions that sits on all 3 of them, in which case it's consistent, but there's infinite solutions. So the next chapter, after we learn how to do row reduction, is going to be about interpreting what the answers say. So there's going to be a lot of parameterize the set of solutions, like what are the sets of solutions, and can you predict the structure of them? That's a good question. All right. So if we're going to be using the idea of these row operations to try to solve systems of equations, we actually need to know what the goal is. I need a goal and I need an algorithm. So the goal is something called row echelon form. So the goal is that we want to turn a matrix into what's called row echelon form. So I should probably tell you what that is. REF. Row echelon form. Has the following definition. So A is in row echelon form if, so a matrix A here, a matrix A is in row echelon form if, one, any rows of all zeros are at the bottom. Any rows of all 0 are at the bottom. The leading entry of each row, which is to say the first non-zero entry as you read left to right. The leading entry, which is also called a pivot of each row, is 1. And 2, any leading entry is to the right of any leading entry above it in rows above. So for a lot of these definitions, a picture is going to be easier than the description of what's going on here. So let's take a look at a couple of matrices that are in row echelon form and then one that isn't. So 1, 0, 1, 2, 0, 1, 2, 1, 0, 0, 0, 0. That matrix is in row echelon form because it has a row of zeros at the bottom. If there is a row of zeros, it has to be on bottom. The leading entry of each row is a 1 as you read from left to right. And every leading entry is below and to the right of any leading entry above it. So this one is to the right of that. So this is in row echelon form. This is in row echelon form. 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1. 1 here. There's a 1 here. There's no rows of 0, so we don't have to worry about that step.
Is that even possible?
Yeah, as a system of linear equations, this would be implicit. This would be an inconsistent system because 0 would be equal to 1. But if it was a coefficient matrix, this would be something that I'd be worried about.
So it doesn't have to be, but
The matrix doesn't have to represent an augmented matrix, and it doesn't have to be square. This is in row echelon form. 1, 0, 1, 10, 0, 0, 0, 0, 0, 0. It's dumb, but that's in row echelon form. All the zeros are on the bottom. There's the pivot, or its leading entry. It's a 1. That's in row echelon form. If I want to go a little bit further, I can define something called reduced row echelon form. If you guys have TI-82s or 84s and you've ever solved the system by using the RREF command, this is what the RREF command is about. All right, so I'm going to erase these because reduced row echelon form so a matrix A is in reduced row echelon form if 1, A is in row echelon form, and additionally, every leading entry has all zeros above and below. Okay, so what I mean by that is if I had something like 1, 1, 1, 0, 0, 1, this matrix is in row echelon form. If also I had that above each pivot, if above, not just below all the pivots at zeros, but above as well, 1, 1, 0, 0, 0, 1, this matrix is in reduced row echelon form. Because now these leading entries have zeros underneath them, but also above as well. More complicated example here might be something like 1, 2, 3, 4, 5, 1, 1, 3, 0, 0, 1, 3, 6. That would be a matrix in row echelon form, but not reduced row echelon form because this pivot has a 3 above it. This leading entry has a 3 up here. Whereas if I wrote down a matrix like 1, 2, 0, 4, 5, 0, 0, 1, 3, 6, this would be the same matrix in reduced row echelon form. Every leading entry has all zeros above and below. So if you think back to the beginning of the class, we at some point had the matrix 1, 2, 3, 0, maybe it was minus 1, 0, 1, 2. That was a matrix that was in row echelon form. And if I wanted to solve the matrix from row echelon form, I wrote down y was equal to 2 and then back solve to figure out what x is equal to, right? So if I wanted to turn this back into a system of equations, I have to use back substitution. Whereas if I continued the process and I ended up with this matrix, this matrix was in reduced row echelon form, and the nice thing about it is I could just tell you what the answers are without substitution, right? x2 is equal to 2, y1 or x1 is equal to 3. So reduced row echelon forms are basically a way of skipping the substitution step when you're solving equations. All right, so the goal of the entire exercise is I give you a matrix that represents a system of equations, and you turn it into row echelon form. You use the basic row operations to start with a system of equations. And if you start with a system and you can reduce it to a row echelon form, you can find the solutions by substitution. And if you go further to reduced row echelon form, you can just read off what the answers are. So, actually, this goes to here's a theorem I can't prove. This related directly to your question. So the last thing we'll do here, I'll give you a definition, a theorem, and then we'll do an example. So definition, A is row equivalent to B if A can be turned into B by row operations. If that's true, we write A tilde B. So that symbol, if I write between two matrices, this little squiggly symbol, I mean A and B are row equivalent to each other. I can use swaps, replacements, or scalings to get from A to B. Here's a theorem I should call Dimitri's theorem, which is, I promise I will come back and prove this when I know what an invertible matrix is. If two linear systems have row equivalent augmented matrices, they have the same solutions. And that's the heart of the question you asked. The reason we set it up this way, the justification for going back and forth, is this theorem. This says, if I start with a linear system and I write down its augmented matrix and I do row operations to it, the solutions never change.
Wait, so that proves
This theorem, I cannot prove this theorem until I can tell you that each row operation is equivalent to multiplying by an invertible matrix. Once we...
what proved what? Like,
What this theorem is going to do is it's going to justify the algorithm I'm going to show you. The proof that this theorem is true, that doing the row operations doesn't change the answers, I can't actually prove that until I teach you about invertible matrices. Okay? You shouldn't believe this necessarily. You might intuit like, yeah, if I change the order of two equations, the answers aren't going to change. And if I multiply one by a scalar, the answers aren't going to change. But this linear combination thing seems like it's doing more, right? If I add two equations together by multiplying one by the other, that seems like it could change the answers. So I can't prove this yet. All right, so here's the actual algorithm. And then what we'll do tomorrow is we'll just practice a bunch of these, because I don't want you guys to get like a C in your physics class because you didn't correctly row reduce a 10 by 10 circuit problem. So this is the algorithm. This is called Gaussian elimination, which you that's a term you may have seen before. And the other name for it is row reduction. So step one. So you start with A. So given a matrix A, put a pivot in the upper left-hand corner. Which really just means make sure there's not a 0 in the upper left-hand corner. This is done by row swapping.
Which there has to be. 'Cause I guess it's-
If there was a leading column of zeros, then the x has nothing to do with the system anyway, and you would just slide over and do it for the second column. Okay? 2, this is an optional step. Scale to get a leading 1. Often easier to do that. Step 3, use row replacement to put all zeros under the leading 1. Step 4, move down and to the right and go back to step 1. Again, easier to show you than to like try to explain what each of these steps are like from the words. Notice here though that the 3 operations, swap, scale, and row replacement, are the engine that drives the algorithm. So let's look at a simple example here. Something like, here, let's do a real quick one. Let's look at 1, 2, how about 2, 4, 6, 1, 5, 10. There's an augmented matrix. And our task is going to be to put that matrix into row echelon form. If you like, you can think about that as representing the equations 2x plus 4y is equal to 6, and x plus 5y is equal to 10. So step 1 says put a pivot in the upper left-hand corner. Well, there's already something there, so I don't need to worry about swapping. If there was a 0 there, I'd have to make sure that a non-zero showed up there, but there's no 0 there. So step 1 is already done for us. It's finished. Step 2, I could scale that to get a leading 1. I can do that. It's optional, but let's take row 1 and we'll replace it with 1/2 of row 1. 1, 2, 3, 1, 5, 10. Step 3, use row replacement. This is what we're working on right now. This is why these are called pivots, by the way. At each step, there's like a pin in that position I'm working with respect to. I'm pivoting off of that entry. So I'm going to put zeros all underneath it using row replacement. Well, there's only one thing underneath it, and I think I can put a 0 there by taking, let's see, I could take row 2, and I could replace it with row 2 plus -1 times row 1. If I wanted to write that out, row 2 is 1, 5, 10. That's row 2. -1 times row 1 is equal to -1, -2, -3. If you add those, you get 0, 3, 7. So that would give us 1, 2, 3, 0, 3, 7. And now it says, okay, we've done step 3. That pivot has nothing but zeros underneath it. Move down and to the right and start again. So now this little box, look in the upper left-hand corner. There's not much of an upper left-hand corner here. It's a 3. There's nothing underneath it. Is this matrix in row echelon form? What's left to be done now?
Scale.
I have to scale it, right? There's not a 1 here. So if I want to scale this, the next step would be to take row 2 and replace it with 1/3 of row 2. And that would get us 1, 2, 3, 0, 1, 7/3. And this matrix is now in row echelon form. It's in, the pivots are leading ones. Each one is to the right of anything that came above. Every pivot has nothing but zeros underneath it, which is what guarantees that you have the down to the right condition. So at this point, if I wanted to, I could use back substitution. So I'm going to run out of time here. The way that we would keep going with this is to put it in reduced row echelon form would be now, at this point, I could take the pivots working from the lower right and make sure they had zeros above. So I could work from this pivot backwards and put zeros above the leading ones instead of below them, and I would get reduced row echelon form. So we'll go through that next time so I'm not jamming it in here. So this idea is powerful and annoying and error prone, and I highly recommend you use computers to do it or your calculators. Wolfram Alpha will do this for you. Double check your work. So tomorrow, I forgot it was open house. I guess I should probably have a quiz anyway. But I was going to do like a lab day quiz like we did last quarter. So I'll just come in with a bunch of problems to work on, a group quiz at the end, just opportunity to practice. All right, see you guys.